Hello everyone, I'm Sharadokayayou and I work at Bristol University under the supervision of Fabrizio Scarpa, and I'm going to talk today about the influence of the humidity on the mechanical properties of 3D printed continuous flax fiber reinforced polylactic acid composites. So I would like to acknowledge DSTL for funding this PhD research. For the study I'm discussing in here, we have printed little squares of continuous flax fiber reinforced polylactic acid. Then we condition this specimen in different boxes with different relative humidity: 11, 35, 54, 75, 98% relative humidity. And then we measure the moisture content, meaning the capability of the material to absorb water. The curve that is presented here shows that the greater the relative humidity RH, the more water is absorbed by the composite. Then we can ask ourselves the following questions. How does moisture influences the general mechanical properties of this material? How does moisture influences the microstructure of the composite and its fracture behavior? But also, how does this material sits among the rest of the literature for similar materials, for instance 3D printed continuous carbon fiber composites? So we've published a paper about this with Fabrizio Scarpa, and the title of this paper is presented at the bottom of every slide of this presentation if you need more information about it. To conduct this study, we prepared different types of specimens, so shear specimen with a plus or minus 45 stacking sequence, longitudinal specimen with 0 degree stacking sequence, and 90 degree specimen for transverse specimen. The quality of this material were tested, especially regarding the measurement of the porosity, thanks to studies that we published previously in composite part A. You can see the title of the study at the bottom of the slide. And then this specimen were conditioned in different boxes with the same relative humidity that I've explained before. And then this specimen were tested in tension on an instrument machine. And these are the curve obtained for the stiffness and its evolution regarding the conditioning moisture content. You can see that all the stiffness measured for longitudinal, transverse, and shear specimen all decrease exponentially. For the shear specimen, the STM standard D3518 specifies that the stiffness for shear specimen are mostly triggered by the stiffness between the flax fiber and the PLA at its interface, and the stiffness of the PLA, so the matrix. There is no information available in literature regarding the impact of the moisture content on the flax fiber PLA interface stiffness, but there is studies that have shown that humidity softens PLA, and this explains the lowering of the stiffness. The same conclusion could be made for transverse specimen, which is mostly triggered, which stiffness is mostly triggered by the stiffness of the matrix. But for the longitudinal specimen, it's a bit different because the stiffness is mostly triggered by the stiffness of the fibers. But when we look at the literature, we see that the stiffness of the fiber usually increases between 0 to 60-70% relative humidity, and decreases between 60-70 to 100% relative humidity. So this cannot explain the stiffness evolution observed here. The reason for this is that we are not really using flax fiber, but more yarn of flax fiber, which are flax fiber twisted together and immersed in a matrix. Another potential explanation is a modification of the interface. Basically, when we immerse the specimen in high humidity, the yarn tend to expand and push the matrix, and modifying the interface between the fiber and the matrix, therefore modifying the entire stiffness of the composites. Other elements have to be discussed, for instance, the impact of water on the polymers inside the fibers, and these are discussed in the paper if you want to have more information about this. But the same kind of exponential decrease evolution has been observed for different types of preparation, such as thermocompression or infusion prepared composites. We also want to indicate that we discuss the influence of moisture content on the strain at failure, and the energy dissipated during fractures, if you are more interested about this test. So now I'm going to talk about fractography, especially for longitudinal specimens, and two C could be were observed. The first one is the energy dissipated during fracture increases as the humidity increases, and the second one, and you can observe on the left side of the slide, that specimen condition at low humidity tend to have straight failure or almost straight failure. We have a specimen condition at high humidity have more zigzag fractures. And this could be explained by the Cook-Gordon mechanism. It's a three-stage process. The first stage, you can see it on the right side of the screen. You have the crack which propagates in the resin in a plane perpendicular to the loading direction. Then in stage 2, this crack is blocked by a yarn. And then in stage 3, two different things could happen. The first one is like if you have a good fiber matrix interface, then the yarn will fracture and the crack will continue to propagate in the same plane that it initially arrived, or a plane very close to it. Whereas if you have a poor fiber matrix interface, then the yarn will debond part of the matrix, and then the crack will propagate along this yarn and will propagate in a different plane than it initially arrived in. And this creates more fracture of the material, therefore more energy dissipated. And that's why for high humidity, when you have a lower fiber matrix interface, you'll have zigzag fractures and more energy dissipated compared to low humidity condition specimen. So here I'm going to talk about the shear fracture fractography that we've observed. So we've tested the specimen with DIC test, digital image correlation, which have highlighted some shear band deformation happening during the test. Those shear bands are synonym with interlaminar fracture between the different plies, because the different plies tend to reorientate towards the direction of loading. And this lead to crack between the plies, and then to entirely fail the specimen, the crack must propagate through the thickness of the specimen. So as at low humidity, yarns are broken, and what you can see on the left side of the screen, basically, if the crack try to go through the specimen at plus 45 degrees, then the yarn at minus 45 degrees will be completely broken in tension. Whereas if we talk about higher humidity condition specimen, then the bonding between the yarn and the matrix, as we said before, is lower, but the interface between two different following filaments are also lower and lowered by the humidity. And therefore, instead of having yarn breaking in tension as we had for low humidity specimen, in that case we have yarn disbonded to matrix and two following filaments peeled from one from the other, and without any breakage, it's just everything is peeled off. And this creates different fracture patterns, but there was no really influence observed on the energy dissipated when measured the energy dissipated during fractures, even though the energy dissipation comes from different mechanisms in that case. So regarding the fracture for the transverse specimen, there was no influence observed of the humidity on the different fracture patterns observed for the specimen, but different fracture patterns have been highlighted, and if you are interested, you can have a look in the paper we published. Now I'm going to finish with comparing our material to the rest of the continuous 3D printed fiber composites that we've been able to propose in here. So you can see that most of them are reinforced with carbon, glass, or aramid fiber, and they are produced with commercially available Mark IV printer and filaments. As you can see on the top left figure, we are very satisfied with our material, which is very close, almost similar to glass fiber stiffness, and not far away to aramid stiffness either, when we plot the rule of mixture for the different types of fiber. We are also lacking something for the test, is the lack of fiber volume fraction. We have fairly low fiber volume fraction for the material that we've been tested, and increasing it would be very useful in order to make it commercially available. We are also lacking information about transverse and shear specimen, because we were the first one to test this specimen in shear and the second one to test in transverse specimen, and more information is required if we want to make a comparison like we did for the longitudinal specimen. And the last thing we were interested in is the repeatability of the test reproduced with in-house produced filament and in-house prepared printer. It was a Prusa printer that we modified to be able to print our material. And we wanted to know if we can repeat our results. And we realized that when measuring the coefficient of variation, we always obtained low values compared to the one as what was available for the other type of material that we are presenting in here. And we are very satisfied with the repeatability that we were able to achieve. So here I'm going to highlight a few of the conclusions that we've been able to make with this study. So the shear, transverse, and longitudinal stiffnesses present an exponential decrease as the moisture content conditioning increases. We are able to observe a constant longitudinal strength for longitudinal specimen, except for 98 relative humidity where it decreases. The strength for transverse and shear specimen were decreasing. As the moisture content increases, there was a constant energy dissipated for shear and transverse specimen, but an increase for longitudinal specimen. Regarding the fractography, higher humidity meant a greater yarn debonding and lower yarn fractures for longitudinal specimen. No influence on fracture for transverse specimen, and high filament disbonding and lower yarn breakage for shear specimen. And finally, we concluded by saying that we have a stiffness which is very close, well, almost similar to glass for our material, but and not far away from aramid reinforced composite either. So as I said several times, we've published a study about this, and in this presentation I've just talked very quickly about everything that we've been doing. If you want more details, please have a read of this paper published in Composite Part. Finally, I would like to thank you for listening to this presentation. Thank all my supervisors and all the people who helped in this study. And you can see with the co-author there are a lot of them. And if you have any question about the test we conducted or any question about the type of material we've been tested, please feel free to contact me with this email address.